All right, so in this video, we're going to talk about curvature, and I've got three curves up on the screen, and you can probably tell that this one is not as, curvy as this one, and this one is not as much as this one. And so we're going to define this now formally using tangent vectors. So if I construct this with tangent vectors, this first one, which almost appears linear, might look something like that. This one, you can see those those tangent vectors start to turn a little bit more. And then on this third one, you can see those tangent vectors turn quite a bit. And so if these are tangent vectors, and let's call them unit tangents, okay? Unit tangent vectors is something we studied in the last video. Then we can now define curvature. We're going to use the Greek letter kappa, and we're going to use S. So we're going to define curvature now as the change of that unit tangent with respect to arc length. Remember, S was that arc length parameterization. So the change in the unit tangent with respect to arc length. So the more that unit tangent changes, the more curvature we're going to have. Okay, so a very intuitive definition. Now, we also need to quantify it because right now we currently have a vector. So if we take the magnitude of it, that's truly going to give us our curvature. Now, because most things are not parameterized by arc length, instead most of the time they're parameterized with t in terms of time, we're going to work with this formula a little bit to come up with an easier way to work. So first thing I'm going to do is I'm going to split this apart using the chain rule. That's going to be d dt, or dt dt, with this guy being our unit tangent vector, times dt ds. So this is an identical chain rule from what you would have seen in Calc 1. Of course, we're taking this guy and we're splitting it apart into these two things. Now, I'm going to rewrite this part essentially by bringing it outside, if you will, and writing it underneath. So follow me on this for a second. Keeping in mind, of course, this is not a vector. This guy right here is not a vector. So that's going to be 1 over ds dt. We still need the absolute value bars on it. I remember there's a difference between the double bars being magnitude and the single bars being absolute value. Curvature is always going to be defined as positive, so the absolute value bars are there. What I've done is, as I pointed out, is I've essentially pulled this guy outside and then went ahead and flipped it so that it's underneath here. And then still next to it, we're going to have this magnitude of dt dt. Okay, again, so that's going to be this guy right here. Okay, now moving into the next step, I want to point out to you guys that on page 769, what I'm about to show you has been discussed. And this is one of these things that I told you to get into your textbook and read. And so this talks about the speed on a curve. And what we decided was that ds dt is the same thing as the magnitude of the velocity vector, okay? And so then I'm going to have dt dt next to it. And so this formula right here is going to be one that's much, much easier to use than needing to use the arc length parameterization. I mean, if you have the arc length parameterization, it's pretty straightforward, but most of the time we don't. Therefore, we've got this guy right here to help us out. Now, here, I'm going to work an example with you guys here in a second, and then afterwards I'm going to give you probably 2 or 3 additional curvature formulas to help you out, because it can get a little bit messy to compute depending on the type or format of the function that you're given. All right, so in the problem we're going to take a look at here, we've got our vector r, and we're going to go ahead and find the unit tangent, we're going to find the unit normal, and then we're going to find the curvature on it as well. So we'll get started here with the unit tangent. And so if you remember, that unit tangent is going to be r prime of t over the magnitude of r prime of t, which is also, if you just want to keep track of things, and this will help here in a little bit, the velocity vector divided by the magnitude of the velocity vector. So those two things have been discussed. Now we're just going to, again, dive in and take a look at an example here again. So my r prime is going to be the derivative of this guy right here. So that's going to be a 12 for the first component. Then we're going to have a 12 over cosine t. back times the derivative of the inside, which would give us the negative sine t. And so if I simplify this, which I certainly would want to, that's going to be a 12 and then a negative 12 tangent of t. Okay? Now, the magnitude of r prime, trying to make that a little neater here. So the magnitude of r prime, that's going to be the square root of 144 plus 144 tangent squared of t. So that was this guy squared plus this guy squared, all square rooted. And then I can simplify that as well. That's going to be a 12 coming out of there. The root 144 is 12. And then if I take the 144 out, I'm going to have 1 plus tangent squared, which is secant squared. The square root of it on the interval here would just give us a secant. So that's going to be what we take now and we divide into this guy right here. So my unit tangent is going to be, again, I'm taking this guy right here, I'm dividing it into both of those. That's just going to give me a cosine for that first component, cosine t. So if I take this and I divide it into there, the 12s go away and I have 1 over secant, which is cosine. Similar here, I'll take this and I'll go into here, leave me with a negative tangent over secant, and that negative tangent over secant can go to a sine. So that's going to be a negative sine of t. Okay, so there's our unit tangent. Now for the unit normal. So for the unit normal, I'm going to go ahead and change colors here so it stands out a little bit. That unit normal, that's going to be your t prime over the magnitude of t prime. And this is the one that gets a little bit messier from time to time. So our t prime is going to be the derivative of this guy. So we've got a negative sine and a negative cosine. And then as for the magnitude of that, the magnitude of t prime, that's going to be now our, whoops, not that, this guy right here. That's going to be a sine squared t plus cosine squared t. So I went ahead, took this guy squared plus this guy squared, all square rooted, and conveniently this one comes out to be a 1, and that's really, really helpful in a problem like this. So then that normal, that unit normal, is going to be this guy right here divided by 1. So 1 is going to be divided into each of those, and of course leaving us with the same thing. So that's going to be then negative sine t, negative cosine t. All right, so that takes care of the unit normal. Now for the curvature. And so I'm going to actually kind of hollow out a spot here on the screen so it's easy to see, because we're going to be using a lot of the same information here. So for that kappa, remember that's going to be 1 over the magnitude of v, and then times the magnitude of dt dt. Okay? Now, we've already got all of this stuff on the screen. The magnitude of v, if you remember, is going to be this guy right here. Since r prime t magnitude is the same thing as the magnitude of the velocity vector, that being the same, this is going to be also equal to our magnitude of v. So I'm going to go ahead and write kappa equals 1 over 12 secant t. Now, if you remember what this means, this is again just different notation. This is the derivative of the unit tangent vector with respect to time. And we've already done that, right? The derivative of the unit tangent vector, and then the magnitude of it is right here. So this guy is also equal to the dt dt. So times 1, and our kappa is nothing more than 1 over 12 cosine t. And much like the derivative back from Calc 1, this is kind of like a curvature predictor. If you want to find the curvature at any given time on the curve, you would plug that in, and then it would spit out the constant, which was, again, the curvature. So kind of a nice example going through it all. As you've worked a couple examples probably by now, looking at these unit tangents and unit normals, in particular the unit normals, these can be a little bit challenging to find, a little bit messy. Conveniently, this problem was set up to where it worked out nicely, but just remember to go nice and slow through these and label everything accordingly, and don't get caught up in the notation. I'm a big fan of writing stuff down like this before getting started. That way it's easier for me to keep track of. All right, so the last thing I want to mention in this video are the different formulas for curvature. A lot of it depends on how the information is presented to you. And so we've already taken a look at this one. These other three here, if you're given a vector valued function, particularly in R3, since we're crossing it, this is another avenue that you could take where you have R prime cross R double prime, the magnitude of it. Remember, we're going to quantify it and it's going to be positive, divided by the magnitude of R prime cubed. Another one down here is where you're given, let's say, just a normal typical parameterization where x equals something and y equals something. Then you can certainly go ahead and use this to come up with what you're looking for. And in fact, I'm going to use this one in the next video, showing you or finding the curvature of a circle. And then finally this one, where we've got our y double prime and our y prime down here. This is generally if you're given a function like y equals f of x, you could find the curvature of it more easily using this. So again, we've done this one. We're going to do this one here in a little bit, and then this one down here we're also going to do in a future example. So I think those generally are the three easiest ones. If you want to explore this one a little bit more, that's great. Otherwise, you can just stick to the ones we've discussed.